So what is a signal? We briefly talked about it a couple of lectures back. We're going to think of a signal as a function that changes with time. So a signal is going to be denoted by x of t, which means t refers to time, and then x takes some value at any given time. So the function x of t is what we will call as a signal. I will likely not use the word, I might use the word function and signal interchangeably. If please pay attention to it. I'm going to use both terms to mean the same thing. Now, we also talked about one thing that may be particularly confusing. We are in general interested in complex signals. What does that mean? That means x of t may refer to a complex number at time t. In my notes, I actually give you some examples for why it's useful to think like that. We also looked at a few examples, but it doesn't hurt to go back and look at a few more examples just to make sure we understand what we mean by a signal. The classic example I gave is an audio signal, right? First one is that if you record music, you can look at the output of your voltage of your microphone, and then that's a function that changes with time. So we can call that as a speech waveform, or as a music signal, or as a signal x of t. The next example comes from biomedical signals. If you have taken an ECG or an EKG or something like that, what they do is they put a sensor on your body, and then they measure voltage as a function of time again, and then you get another waveform. So that's another signal that we may be interested in. The third signal that you might be interested in is when you talk on your phone, or when you upload a photo from your phone. There is an antenna on your phone. The antenna is sending a signal to the base station or to the Wi-Fi router, right? So typically what you want to do is you want to upload a photo. A photo is like a bunch of pixels. But you can't really transmit pixels out of your antenna, right? So what gets transmitted out of the antenna is actually an electromagnetic signal. These pixels somehow get converted to a waveform, and then the waveform gets transmitted out of the antenna. So that waveform is a signal for us, because that's something that changes with time. And you can see in all these cases, these signals carry some information. Like in the case of the picture, uploading a picture, clearly the picture is the information that you wanted to send, but you convert that to a waveform, because waveforms are what you can usually transmit out of antennas, right? So So a signal is typically something that carries information. There is some information in the signal. Number 4, the closing price of a company's stock on each day, right? If you think about that, this looks like it's slightly different from the first 3 examples, and let's think about why it's different. Because if I'm thinking about the stock price at the end of the day, then my time axis now does not change continuously. Like for every day there is a price, right? It's not meaningful to say what was the price at 8 o'clock, because that's not how I'm defining my signal. I'm defining it to be the stock price at the end of today. So the difference between example 4 and the past 3 examples is that in example 4, time takes only integer values, whereas in the first 3 examples, time can take any real number as its value, and there is a value for the signal at that time, right? So we call examples like number 4 as discrete time signals, whereas the first 3 we call them as continuous time signals. And here is something else which you might not think of as actually a signal, but indeed it's a signal. Think about how you're using ChatGPT. So you go type some question to ChatGPT, right? And then you get some response from ChatGPT. But what actually happens when you type a question, type some text to ChatGPT, is that this text is first parsed, into small units of words. Like, the whole text, it gets parsed into little units. They're called tokens. And what they do is they have a giant dictionary, a dictionary of 50,000 tokens. So they take each one of these tokens and then they associate a number, which is the token number in the dictionary. So for example, short words like a and the, commonly occurring words, letters, they're all tokens in the language. So they parse your prompt into a bunch of numbers. And these numbers get processed by ChatGPT and then you get some response. But think about the prompt as a sequence of tokens. That's actually a discrete time signal, right? Because you have token number and then there is a value for the token at each time. And this is actually what's fed into this giant model that ChatGPT uses. And in fact, we'll think about ChatGPT as a system when we talk about systems later on. So ChatGPT does what is called as auto-regressive generation. So what it does is it generates one token at a time and then uses that token back as input. So it's just like how you would write. When you would write text, you would write one word or one letter at a time and then think about what should be a good next word to write, right? So it's like you have a signal. The signal, you're adding one element to the signal at each time. And this is called as an auto-regressive system. We'll talk about that a bit later. But you can see that the input to ChatGPT can be thought of as a signal. We talked about photo or image being a two-dimensional signal. Right. So now we wanted to quickly talk about the difference between a continuous time signal and a discrete time signal. Like I mentioned, in a continuous time signal, t changes continuously. In a discrete time signal, the time takes only integer values. And the difference in the notation, it's important to follow. We are going to use x of t within curly brackets, parenthesis, to denote a continuous time signal. Whereas if it's a discrete time signal, we're going to use square brackets. And instead of t, we are going to use n to denote time. So just get used to the difference between x of t versus x of n. So I think I mentioned this earlier. I really like drawing things. I think it's very insightful to draw things. Whenever you can sketch signals, you should approximately try to sketch signals. So if we were to sketch a discrete time signal, a discrete time signal would typically look like this. What I mean by that is, since time takes only integer values, you would typically not use a continuous plot, but you use what is called as a stem plot. In Python, if you were to plot something like this, you would use a stem plot, which means for every value there is a line that comes from that, right? So when you see something like this, this is a discrete time signal. Does that make sense? A continuous time signal, on the other hand, you might get a plot like this, right? Because t is changing continuously. For every value of t, there should be some value taken by x of t. Does that make sense? Okay. Now let's look at this picture. We talked about continuous time signals. We talked about discrete time signals. Quite often, these discrete time signals are actually obtained from continuous time signals through a process called sampling. So what do I mean by that? Usually you have a continuous time signal, which you can see here is that black signal over there, right? Now, what we may do is we may just choose to keep the value of this the signal only at certain time instance. In this case, what I'm saying is, I'm going to look at the signal and see its value at time t sub s. I'm going to note down its value, and that's the value. And then I'm going to look at the value of the signal at time 2 times t sub s, 3 times t sub s, 4 times t sub s, so on and so forth, right? So I'm essentially taking samples of the signal periodically, and those values, if I just think of now time as being saying, okay, that's the first sample, then I have a second sample, third sample, so on and so forth, then I get a discrete time signal. So there is a way to convert the continuous time signal to a discrete time signal, and this process is called sampling. Do you have any, yeah?
If we just sample, if we have a certain sample rate, wouldn't that technically mean that it's discrete, but we're like smoothing it out?
What do you mean by we are smoothing it out?
Like, it's technically the same as the discrete signal, but we like to draw the lines in between to demonstrate.
So I didn't draw the lines yet, right? All I am trying to say, so think about you having your music on your, or let's say you have Spotify, right? How does Spotify store the music? Spotify is not storing that continuous time waveform, right? The original music was continuous time waveform. What they did is they took the waveform, they took 44,100 samples per second.
Right.
So now your T sub s is 1 over 44,100. You get a bunch of real numbers. You only store those real numbers.
Right.
So that is a discrete time waveform, right? I think what you are saying is, well, it's never enough for me to look at the discrete time waveform because I ultimately want to listen to my music, which is a continuous time waveform. I have to do something to my discrete time waveform, signal, to obtain my continuous time waveform back. And for that, if you're saying, oh, if I just draw lines between these things, that's not exactly the same signal. That's just approximating the signal, right? That's what you mean.
Yeah.
Or maybe drawing lines isn't the best thing to do.
Okay.
And that's what we're going to see towards the end of the class, that it's indeed not the best thing to do.
Okay.
There is a better way. In fact, now is a good time to think about it, right? I give you these samples. Like he said, we have lost all the information in the signal between the times when I took samples. How should I interpolate between the samples if I want to get my original continuous time signal back? When you want to listen to your music, you want to listen to the continuous time waveform, right? You don't want to listen to discrete things. How do you get that back? You have to interpolate between the samples, right? You have to somehow fill in the values between the samples. Yes, drawing lines, maybe it's one natural way to think of it, but it turns out to be not the good thing to do, or at least not the best thing to do. It turns out there is a better way to do the sampling. It's called as sampling with a sync function. We'll look at it, see why we should do that, so on and so forth. Okay, that's a good question. By the way, are there any audio files here? Have you familiar with the new high fidelity audio recording standards, like the DSD type of thing?
I've watched like one YouTube video on it. More of the, I just have a bunch of like shitty old stereos and like WAV files.
Yeah, so something really interesting is happening. Like when you do CDs or MP3s, things like that, we typically sample music at 44,100 samples per second. But now people are interested in very high fidelity audio, so they're sampling it at like crazy high speeds samples. And there is something interesting about this. Maybe we'll talk about it towards the end of the class, why it's better to do something like that. But yeah.
You're talking about WAV files?
What files?
WAV?
No, WAV is not what I'm talking about. So WAVs are typically obtained by just sampling at 44,100 kilohertz and then writing down the real number using 16 bits of precision. So in 248, do you talk about representing numbers with certain bits of precision and stuff like that, right? So usually wave is like you sample. When you sample, you get a real number. You cannot write a real number onto a computer, right? You have to use a certain number of bits of precision. So they typically use 16 bits of precision, and that's what the wave format is. Now, what MP3 does is MP3 says, okay, the wave format is too big. I'm going to try to compress it somehow. And I'm going to compress it. I might lose some quality when I do the compression, and that's what gives you MP3. But so wave is an uncompressed format. MP3 is a compressed format.